Yeah, because, well, they're at, I don't know where Madeline and Gareth are, but Sam and Parker at the theater thing. So,
Garland's probably sick. He's really past high school.
I don't know. I feel like everyone was feeling sick yesterday.
it's going around. Like, I mean, I'm finally feeling, like I said, I feel a little bit better. And I went and I taught a class and then I stayed for another class. And yeah, pretty much had to blow my nose 975 times in that hour and a half. So, it's what it is. Okay. All right, so let's take a look at our warm up. So it says the graph of the function f is shown below, above. Let g be the function defined by g of x equals the integral from 1 to x of f of t dt. At what value of x in the interval from 0.5 to 6.5 does g have a relative maximum? Okay. What are we thinking? We're not thinking. Okay, if we're looking for a relative maximum, that comes from a derivative. Okay, so if we take the derivative of g, what's that going to give me? F of x. We'd plug that x in right there. So g prime at x is f of x. So this graph is going to tell me where we have a relative maximum on g. We'll be looking for where that graph changes from positive to negative. Okay, and so where does it change from positive to negative? Negative, positive. It happens at 3. Okay, so my only answer is 3. Question about that? We started that yesterday with maximums and minimums and all the good things. Okay, alrighty. So here's your affirmation. Nobody can go back and start a new beginning, but anyone can start today and make a new ending. I like that one. Maria Robinson. All right, so we're going to do a small investigation to start, and then I think it's got like 7 questions, and we're going to get into what we're talking about today, which is part 2 of the fundamental theorem, which is going to allow us to evaluate definite integrals, and I like to put algebraically. All right, so we're going to do a bunch of algebra today. All right, so here we go. Nadine's training for her figure skating competition. Her velocity, v of t, is given by that equation, negative t squared plus 6t plus 1, between 0 and 5, where v of t is measured in meters per second and t is measured in seconds. So go ahead on. Let's work on that. Everything good? Yeah. Okay. You can work with Oakley if you want to, since y'all don't have partners today. Despacio.
Oh, it's a goal, sorry.
How do I get the, alphabet?
I think the math is the reason why we're all sick.
The calculus is making you sick, huh?
See, just,
It happens.
I think we get after. I don't know how it is. I just say no. I just say no for you.
You said no.
I just say, let it go.
You can do it.
There wouldn't be nothing. Justin, hello. I just wanted to say hi. I do that for the
That's not, I'm sure that's wrong.
It is a possible.
It isn't possible.
But I was just about right.
Who you gonna play tonight? Oh, Riverdale, that's right. I can't remember. Yeah, at least it's not a region game.
He's not. He's singing those songs.
I feel that. Gotta play it one more time. Okay. Hopefully some interesting things came out when you were working on this. This is my husband's favorite Kansas City Chief of all time, Derek Thomas. He's no longer alive. If we had had 2 boys, our second boy would have been named Derek Thomas. So now we're just gonna maybe get a dog one day and call him DT. So. Some kid walked down the hall a while ago and did the Dirty Bird. Like did the eagle wings. It was funny. I was like, well, good for you, buddy. Well, I'm excited for I always love to eat during the Super Bowl, so I'm trying to decide what we're going to make. I'm feeling buffalo chicken dip because that's always good, and I can make that so that it's healthy-ish or, healthier-ish. Anyway, so I'll probably do that, and I have a really good homemade chocolate chip gluten-free cookie recipe, so I may make some gluten-free chocolate chip cookies. Maybe some hot wings. I don't know. I love wings. Pigs in a blanket. I mean, all the good snacky foods. Did y'all get caught out in that crazy rain yesterday? It was insane. We were in the gym and it has a metal roof and you couldn't even hear the music from how loud the rain was. It was insane.
My mom was trying to take pictures. Multiple times on the way home, the stream had come up over the road.
Yeah.
She was trying to take pictures of it, but the rain was so heavy that you couldn't.
Oh my gosh, couldn't even see it. How about White House High School flooded and their teachers have to go clean the building this morning? Yeah, and they have coming home this tonight, so crazy.
They did that last year too.
Yeah. Did you get a new bottle?
For Christmas.
Oh, okay. I mean, that's what I meant. It's different than the one you had in the fall. Yeah. All right, so let's talk just a little bit about what all was going on with Nadine and her figure skating. So they gave me this velocity function, negative t squared plus 6t plus 1, all right, from 0 to 5. And so it asks to describe her velocity. Well, think about that velocity function, what it looks like. All right, so if this is t and v of t, all right, so it's, looks like an upside down parabola. So how could we describe what her velocity is doing? Yeah, so the velocity increases till it reaches the maximum, and then it decreases. What's her initial velocity? Yeah, it's 1. Increases, then decreases. We get initial velocity by plugging in what for t? 0. So her initial velocity was 1 meter per second. Okay, so then it asks you to interpret the integral from 2 to 5 of the velocity in the context of this problem. So if we're thinking about that, let's put our axis right there. If we're going from 2 to 5, all right, what's that integral going to tell me? Yeah, that distance that she traveled, okay, the meters she accumulated. It's our accumulation function. It's the meters or the distance accumulated. Between 2 and 5 seconds. So then it gets sweet to me and it says, hey, use your calculator. Evaluate that integral using Math 9 on your calculator. What do you get when you do that?
27.
Yeah, 27 meters. Okay. So in that length of time, she went 27 meters. So now I like number 3 because it says give a possible function for position. All right, in meters from one end of the rink to the other. Basically, we want to go backwards. V of t is the derivative of position, so we need to go backwards. So let me write v of t down, and then we'll just talk through it. Negative t squared plus 6t plus 1. So when we think about her position, okay, what would I have had to start with to end up with a t squared to start with? A t cubed, okay? But I need my coefficient to be a -1. So what does the coefficient of the original function need to be? -1/3. Okay? Let's look at the next term. All right, I want to end up with a 6t. Well, what did I have to start with to have just a plain t? Yep, t squared. And then if I need my new coefficient to be 6, what did I have to start with? 3. Okay, 2 times 3 is 6. All right. And then to end up with just a 1, what did we have to start with? A t, okay? Now, could there have been something else at the end? Yeah, we could have had some kind of constant out there, okay? So, pick a number, right? Because the derivative of that number would be 0, which wouldn't be in your position function, okay? So I want every table to pick a different number if you haven't already, okay? I'm going to pick my favorite number, 27.
4.
Okay, so just pick a number, all right? Because it doesn't matter. If we take the derivative of that number, it would be 0, so it would work. Okay, so those are our possibilities. Now, let's look at what it asked me to do next. Okay, that's what it asked me to do next. And this is where things are about to get fun. Okay, so it says to find the change in position between t equals 5 and t equals 2 and t equals 5 using your equation in question 3. Okay, so take your equation. All right, so I had s of t equaled -1/3 t cubed. We're going to use our calculators. Plus 3t squared plus t plus 27. Okay, and I want to do s at 5 minus s at 2. All right, so take a second and do that. Use your calculator. All right, so we're just plugging in, finding that change in our position. Okay. Might be easier to get each individual number and then subtract, so. You don't have a boot on. It's a good day.
Yeah.
Sorry. I guess I didn't see you walk in this morning.
Yeah, not behind you.
Okay. Snicker. All right. Solomon's group, what'd y'all get when you did that?
I get 47.
27. All right. Larger walk, what'd y'all get?
27.
Oh, what'd y'all get back there in the back corner? Yeah, 27. Himmel, yeah, Oakley, sorry. You get 27, okay? We get 27. So what's that mean is true about our answers in number 2 and number 4? They're exactly the same, okay? That is not a coincidence. All right, what that's telling me is that the integral from 2 to 5 of v of t dt is the same thing as the position at 5 minus the position at 2. Okay, they are equal. All right, they are equal. And that is the fundamental theorem part 2. Okay, that's what's cool about that. Inside the integral, we have a derivative. All right, And then S would be what we would call an antiderivative. All right, it's the antiderivative, or what we started with. Now, on number 6, it says at t equals 2, she's 12 meters from the edge of the rink. Where is she at t equals 5? Okay, so at t equals 2, she's 12. All right, at t equals 5, so from 2 to 5, how much distance did she cover? 27. And so her total distance there was what, 39 meters? Okay. So what we did right there is we took S at 2 and we added that integral to it. Okay, that's what we did. Those are the same things. All right, they gave me the position at 2, and then we did the accumulated change after 2 to get all the way to 5. Okay, now the last thing they asked me to do is to find her actual position function, because we just had 4 or 5 different answers in terms of what her position function was, but we all got the same accumulation. All right, so let's try to figure out what is her actual position function. So here's what we're going to do. We're going to take that S of t function that we had, and instead of a number at the end, we're going to put a variable, all right, because it can change. So I have negative 1/3 t cubed plus 3t squared plus t, and we're going to call it plus c. There's a constant there that we need to find, okay? We need to find it. And we're going to use this information right here, this initial condition. They told me at t equals 2, her position was 12, okay? So they gave me that S at 2 was equal to 12. We're just going to plug that in and solve for C. Okay, so we're going to plug that in and solve for C. I'm going to give myself enough room right there, or y'all. All right, so we would have 12 is equal to negative 1/3 times 2 cubed plus 3 times 2 squared plus 2 plus a constant. I'll let you do all that math. All right, but I think we get C equals 2/3 when we work it all out. Okay, so that her actual position function then, S of t, is negative 1/3 t cubed plus 3t squared plus t plus 2/3. Okay, because we've got what, negative 8/3, 12 plus 2. The 12s would cancel out. They give me 10. Yeah. Okay. We refer to this as an initial condition problem. Basically, you're just figuring out what is that constant, okay? And that's going to come up more next week, all right? Today, we're going to focus right here, all right? We're going to focus right here today, and that's part 2 of the fundamental theorem, okay? So again, we've got a function that's continuous, and g is an antiderivative of that function, okay? Then they say that the integral from a to b of f of x dx is g evaluated at b minus g evaluated at a. Okay, g being the antiderivative. In other words, this is how I like to think about it. Okay, if we have the integral from a to b, inside that integral is a derivative. To evaluate that integral, we find the original function evaluated at b minus the original function evaluated at a. Okay, so that just makes it, to me, a little bit easier to figure it out. We have to consider what's inside the integral as a derivative. We have to figure out what we started with, and then we plug in. The nice thing about these is we don't have to worry about that constant at the end. If I'm plugging things in, the constant did not matter, okay? So we don't have to worry about it. We don't have to plug in that thing that we got to choose, okay? So we don't have to worry about it. right? So let's apply it, all right? Lots of algebra moving forward, okay? And thinking about functions and their derivatives and all that good stuff. Okay, so putting all of our calculus knowledge to good use. Once we get here, it gets fun, all right? This is the key part of integration, all right? So let's look at number 3. We'll look at it together. We'll do these first 2 together, and I'll let y'all practice. So it says evaluate the integral from 1 to 4 of 3x squared dx. The first thing we need to find is the antiderivative. In other words, what did I start with to get 3x squared? X cubed. Okay. Now, what they'll do is they'll put a bracket around it. Okay. And then they'll put those boundaries in the same place. Apparently, if you write. There it is. Okay. So now what we're going to do is we're going to take the boundaries, plug in the top, minus, plug in the bottom. And that's how we evaluate that integral. Okay. So 4 cubed is what, 64? Minus 1 would give me 63. All right. That's the value of that integral. Okay. This is referred to as a definite integral because it has a definite value. We have numbers to plug in. Okay. Let's look at the one underneath it. Okay. Remember, what's inside is the derivative. Okay. So if my derivative was cosine, what did we start with? Sine. Okay. So I've got sine of t, and I'm going to evaluate it from 0 to pi over 2. Okay. So we literally plug in that top boundary into the function and the bottom boundary into the function. Okay. What is the sign at pi over 2? It's 1. And the sign at 0? 0. So my answer is 1. Okay. Part 2 of the fundamental theorem. That's in its most basic form. You knew it was coming. You knew it's getting spicy. Okay. You just know. Y'all know me well enough. Okay. Y'all try those next 2. All right, at the top of the next page. These are almost always non-calculator. So if you get fractions, don't panic. You're just going to have to figure it out. Algebra. let's look at that first one, then we'll talk about that second one. That one's a little tricky with that square root in there, okay? So with the first one, let's get our original function first, okay? What did we have to start with to get an x to the third? X to the fourth, but we need the coefficient to go away, so we need a new coefficient. What's it going to be? 1/4, okay? To end up with a plain 1, when I take a derivative, what did I start with? And I don't know what I did right there. So plus x, all right? We're going to evaluate it from -1 to 3. Now, be careful, because it's usually, once you get here, it's going to be in your arithmetic if you mess up, okay? So I'm going to have 1/4 times times 3 to the 4th plus 3 minus 1/4 times -1 to the 4th plus -1. All right. So the arithmetic gets a little tricky. 3 to the 4th, is that 81? Yep. 81 over 4 plus 3 minus -1 to the 4th is going to be 1. So it's going to be 1/4 minus 1. So I'm just going to keep doing it. 81 over 4 plus 3 minus 1/4 minus 1. That would be what, a -3/4? Okay. So minus is going to be plus a positive. So now here's what I'm going to do. I'm going to make everything a fourth. So I have 81/4, I have 12/4, and I have 3/4. All right. And if we add all of that together, okay, 81 and 12 will be 93 plus 3. That'd be 96 over 4. And I believe that divides, doesn't it? 24. Yep. All right. So just a lot of arithmetic. Walk your face. What question do you have? See if you can find a spot.
I got the answer.
Okay.
It's just the algebra. The algebra's gonna be something.
It is. It's going to be something. Okay. Let's look at the next one because it's going to get even more interesting over here. Okay. So think about this one. I have 3x to the 1/2. Now that's just my thought bubble up here. Okay. That is inside of my integral, right? If we think about an antiderivative, okay, what did I have to start with so that I ended up, when I took a derivative, with 1/2? 3/2. Okay, so it's x to the 3/2. Now, I want to end up with just a coefficient of 3. So what had to be my coefficient to start? 2. Yep. 3/2 times 2 would give me the 3 that's inside of there. So we're going to evaluate from 1 to 4. Okay. So I have 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. Okay. 4 to the 3/2, that means take a square root and cube it. Okay, take a square root and cube it. So what's the square root of 4? And 2 cubed is 8. Okay, 1 to any power is just 1, thank goodness. So I have 16 minus 2, which is 14. Okay, so you just really have to kind of think your way through those radical ones. All right, thinking about your powers. Okay, when we take a derivative, we subtract 1. What does it look like we're doing when we do that integral to get the original function? We're adding. We do the opposite thing, right? So when we take a derivative, if I start with x to the 3rd, I subtract 1. Okay, but if I have the derivative and go backwards, I add 1. So it's just, doing the reverse. All right. Now, I want to do this one with you because what's different about this one from the other ones? Absolute value, okay? And if you remember, absolute value is a tricky heifer, okay? Because we can't just take the antiderivative of what's inside that parenthesis, okay? We got to think about what's really happening with my absolute value. So remember, with absolute value, I'm going to come over here and do a thought bubble, okay? By definition, absolute value, all right, is equal to x when x is greater than 0 and the opposite of x when x is less than 0. Okay? because we got to do a positive side and a negative side. All right. The same is true when it's inside of an integral. Okay. So if I have the absolute value of 2x minus 1, okay, it is 2x minus 1, or it's the opposite of 2x minus 1. What we have to figure out is where would that 0 point be, where the absolute value would change. Okay, so where would 2x minus 1 equal 0? At 1/2. Okay, so this is when x is greater than 1/2, when x is less than 1/2. Okay, so when we go over here and we look at this integral, it wants me to do the integral from 0 to 2. Okay, 1/2 falls in the middle of that. So we're going to use both pieces of this absolute value. Okay, the first piece is going to be from 0 to 1/2. Okay, so is that the positive piece or the negative piece? The negative piece. Okay, so that would be the opposite of 2x minus 1. Well, I'm just going to rewrite it as negative 2x plus 1 dx. Okay, so I'm going to have to take two integrals to do it because absolute value is split into two parts. Okay, my next integral that we're going to do is going to start at 1/2 and go to my top boundary, which is 2. And that's going to use the positive piece, so the 2x minus 1 dx. Okay, so let me stop right there. Let's make sure we understand what I did and why I did it. Right? Anytime you take an integral with absolute value, you're going to have to split it if the 0 point, or like that, if you think about absolute value, the v, if that vertex point is in those boundaries somewhere. Okay? And we find that by taking what's inside the parenthesis and setting it equal to 0. Okay, or inside the absolute value. Right? Now we're going to do it the same way we've done everything else. Okay, so let's start with the first piece. Let's take an antiderivative. What would I start with to get a negative 2x? Yeah, and to get a 1, x. And we're going to go from 0 to 1/2. Okay. The next side, what would I start with to get a 2x? X squared. And to get a negative 1, minus x. And our boundaries are going to be 1/2 to 2. Okay. So we're going to have a lot of evaluation in here in a second, okay? A lot of arithmetic. Because we got fractions, we're going to have fractions, okay? Luckily, they're halves. Okay. So let's start over here. I want the opposite of 1/2 squared plus 1/2 minus, oh, look, my favorite, the opposite of 0 squared plus 0. What's going to happen there? That whole thing is gone. Praise the Lord. Okay. Yes, sometimes we get really excited. The next one, let's plug in the 2. So I'm going to have 2 squared minus 2 minus 1/2 squared minus 1/2. And I did keep all that in parentheses. We have to be careful because we'll drop a negative at times and that can get confusing. All right, so let's do some arithmetic. The opposite of 1/2 squared would be negative 1/4 plus 1/2. Okay, I lost the 0 parenthesis, thank goodness. 2 squared would be 4, minus 2 would be 2. Okay. Minus, I'm going to keep this one in parentheses for just another second. 1/2 squared would be 1/4 and minus 1/2. Okay. Now, if I distribute that negative into that last parenthesis, we're going to get a negative 1/4 plus 1/2 plus 2 minus 1/4 plus 1/2. Okay, I did it on purpose. All right, I left it all fractions for a second on purpose. Okay, what's my 1/2 plus a 1/2 going to give me? 1, and I'm going to add 2 to it, so what's my whole number? 3. And then I've got a negative 1/4 and another negative 1/4. That's a negative 1/2. So I have 3 minus 1/2, which is 2 1/2 or 5 over 2. Okay, so your fraction arithmetic's going to get really good, people. Okay, it's going to get really good. The good news is that I usually don't do much more than 8s, so there you go. All right. What question do you have besides can we just not do it?
Stole my question.
Do what?
Stole my question.
Oh, sorry. After 28 years, I get pretty good at anticipating. We interviewed a math teacher yesterday, and she, I'm just so old, y'all. I'm just 100. When we told her that I had been teaching 28 years, I wish you'd seen her eyes. It was like I crawled out of I was Yoda at that moment, you know. Gonna die any moment, but can still work a lightsaber, you know. Anyway. Okay, let's look at this one. Do what? She was great. I told Dr. Becker to offer her the job. Probably Algebra 2. So.
Did you interview her second book?
Yes.
Okay, yeah.
Yeah. She's really, I really like her.
She's very sweet.
Yes. And she's girlfriends to a kid I taught, so that's even crazier to me. I'm like, what? All right. So here we go. So the graph of y equals f of x is shown at the right or the left. What is the integral from 1 to 3 of f prime of x dx? Now, think about what that integral means. Okay? And how could we answer that? What would be the antiderivative of f prime? F. And we're going to evaluate it from 1 to 3. So what I need is f at 3 minus f at 1. Do I have what I need?
Yes.
Yeah, they're just those y values on the graph. Okay? F at 3 was 6. F at 1 is 2. My answer is 4. Okay? Don't be surprised if they throw something like that, as simple as that, in a multiple choice. Okay? They will give you some gimmies along the way. All right? Which is nice. Okay? That's just really nice of them to do that. Okay? All right, let's look at some multiple choice. All right, calculator and non-calculator. And what happens, just want to show you lots of different things. Okay. Woo, it's a table. You knew it was coming. All right, we've had a graph. Now here's a table. All right, it's what they do. Okay. Play with that one for a second. See if you can figure it out. Y'all are really quiet without those four.
Wonder who makes up most that.
You got a theory?
It is the theater place, I thought.
That is true. That is true. They can't help it. It's just in them to be them. Okay. So we're evaluating this integral, all right, of f prime, which means I need my antiderivative, which would be f, evaluated from -4 to -1. So I need f at -4 minus f at -1. Okay. So f at -4 is 0.75. f at -1 is -1.5. So we would add the opposite thing. And what would we get? Oh, wait, I did it backwards. Did I do it backwards?
I think something just -1 is odd.
Yep, I did. I was like, wait a minute, I did it backwards. Okay, here we go. -1, there you go, it's on top. Perfect, Newton. Minus f at -4, there we go. We pull it from just the f column. Notice they put multiple things on there, that's to trick you. Okay, so they want you just to use the appropriate row, but they'll put more mess on there than you need. So -1.5 minus 0.75, there we go. And we get -2.25, which was B. Okay. That all good? Okay. Now, let's look at this next one. This one is a calculator active question because the number that's on it, it's 81, all right? And that's where we see a lot of our theory-based math, okay? And so here's what it tells me. It says that g of x is an antiderivative, all right? That means I took, it's an antiderivative for f of x, okay? So which one is the actual derivative, f or g? F. Which one would be inside the integral? Also F, okay? So F is the derivative, so it would be inside an integral. That's important to know. Okay? So if we're looking for the integral, actually, let's go back a little bit. All right, so it wants me to find g at 4. Okay, it wants me to find g at 4, the antiderivative evaluated at 4. So we got to think for a little bit just about what's going on, okay? When g is 2, all right, so when the antiderivative is 2, the function is -7, so that's something we've been given, okay? That's something we've been given. So if I do the integral from 2 to 4 of f of x dx, we know the antiderivative is g of x. That's what they told me, okay, that we would evaluate from 2 to 4, okay? So this integral is equal to g at 4 minus g at 2. Okay, that's what the fundamental theorem says. If we're doing the integral from 2 to 4 of a derivative, the antiderivative evaluated at the top minus the antiderivative evaluated at the bottom. What I want to do is solve for g of 4 because that's what it wants me to find. Okay, well, do I know what g at 2 is? It's -7. So I have the integral from 2 to 4 of f of x dx equals g at 4 minus a -7 or just plus a 7, okay? If I wanted to get g at 4 by itself, who needs to move? The 7. It's going to move over here to the front and become a -7. So E is my correct answer. Okay. Question about that one? All right, see if you can do the one underneath it. Bless you. you do. Okay? Another way to think about that, if you don't want to do all the work, okay? If they give you one of the values and an antiderivative, that value goes in the front plus the integral of what's left over. Okay, from that point forward. And again, we'll talk about that again in a day or two and just kind of bring that all back into focus. Okay, but remember, it comes from the fundamental theorem. Is where it's coming from. If we know the derivative and it's inside the integral, the antiderivative evaluated at the boundaries, we just subtract. Now, this next one I really like. All right. The graph of G prime is given below. All right, so this is not G, this is G prime. It's different, okay? If G at -2 is equal to -11, find G at 4. We're going to have to look at some accumulation, okay? So if I take the integral from -2 to 4 of G prime at X, okay, that's going to equal G at 4 minus G at -2. Okay, that's what it's going to equal. All right, so just like we did a few minutes ago, we know this G at -2 is -11. So we would pull it over here to this other side. 4 of G prime of X dx, and this would give me G at 4, all right, which is what I'm looking for. The problem is I don't have a way to evaluate this integral, all right, using values because I don't know what G is. I just know G prime, okay? So what have we been doing when we couldn't use algebra to evaluate an integral? We did area. Okay, and that's what we're going to do for this integral. I need the area from -2 to 4. Okay, the good news is all that area is positive, but what shapes do I have? Semicircle and a triangle. Okay, if I had the G function, we could have used the values, but I didn't have that. Okay, I had G prime, so I'm going to keep the -11. The semicircle, 1/2 pi times the radius, which was 2, and squared, plus the triangle, 1/2 the base times the height. So that's going to give me -11 plus 2 pi plus 2, or -9 plus 2 pi. That is the exact value of G of 4. Okay, so if you don't have the G function, you're going to have to use the area, all right, if they give you the derivative. Question about that one? That's a good question. That will all, again, there are certain things that we can pretty much count on are going to show up at some point on the test, and this is one of them. Okay, maybe in a free response, maybe in a multiple choice, but it will show up where you'll have to use area. Okay, in conjunction with the fundamental theorem. It's just crazy. All right, so the main application of the fundamental theorem is this, okay, is that it is an application that if we take the integral of a rate of change, okay, gives us net change. Right? So the integral of a rate of change will give us net change. How much did something change, right, over the course of what we were doing? Okay. The good news is for a lot of these problems, we get to use a calculator. All right. Some we don't, but for some we do. Okay. All right, so let's look at this one. It says the fixed cost of starting a manufacturing run and producing the first 10 units is $200. After that, the marginal cost of at X units output is dCdx equals 100 over X squared. Find the total cost of producing the first 100 units. Okay? How many units did they give me a fixed price for? 10. Okay? So we know we're going to start at $200. That's given. All right? But once I hit 10 units, it has a rate of change. Okay? So I'm going to start at 10 on my integral. Where do I want to stop? 100, because I'm producing 100 units. Do I have a rate of change to put in there? Yep, that dCdx. So we're going to do 1,000 over X squared dx. At this point, I'd pick up my calculator and type it in. Okay. You out of lead, Justin. Oops. Do you need lead? Oh, okay. What'd you get? $290. That's it. Okay, that's it, which is nice. Right. So the other day, we did this problem in our notes. I don't know if you remember. Okay, and I left out part B. Okay, here's why. Because it dealt with part of the fundamental theorem that we hadn't discussed yet. Right? So it's just the temperature in the bathtub, all the things. The water's heated for 30 minutes, beginning at time 0. Selected values for the first 20 minutes are given in the table. Okay? Use the data in the table to evaluate 0 to 20 W prime dt. Using correct units, interpret the meaning in the context of this problem. And this is where, okay, so an actual released free response question, where we come in. So let's talk about evaluating the data using the table. Okay, so the integral from 0 to 20 of W prime t dt, okay, says I need the actual function since I started with the rate of change. So I would need W at 20 minus W at 0. Okay, are those values in my table? Yes. So 71 minus 55 would give me 16. So now let's talk about what that means. All right. An integral gives me accumulated change. Okay. So we would say this is our justification. All right. And writing it in context. We're talking about water and the temperature. So the temperature of the water changed by 16 degrees Fahrenheit. We want to use the appropriate units. The first 20 minutes. Okay, so that's our explanation. All right. Okay. Now for part D. This is the actual part D, by the way. All right. So between 20 and 25, the function W that models the water temperature has a first derivative given by W prime equals, you got all that stuff. Based on the model, what is the temperature of the water at time t equals 25? Okay, this is a calculator active question. All right. So we want to find out the temperature of the water at time equals 25. Do we know how much it changes at 16? Okay. I mean at 16. For 20, we know that rate of change, right? But if we want to get the total amount or the total temperatures, which we're getting there, all right, how much was it at time 20? It was 71, okay? Then we got to accumulate the change from 20 to 25, okay? Or the temperature from 20 to 25. So 20 to 25 0.4 square root of t cosine 0.06 t dt. Right? And we would use our calculator. If memory serves me right, you got a point for the integral part of this, okay? But you had to have it in the proper form, which meant the dt at the end, so don't leave that off, okay? Okay, because it's asking me for the actual temperature, we start with our last known temperature and then add on the change. Okay, so that's what we're using. And we use our calculator. I think you'll get 73.043. All right, that one was calculator active, okay? Because it's numbered 1. All right, 1 and 2 are calculator active. 3, 4, 5, and 6 are calculator not active, okay? All right, let's do one more. Calculator active, released free response. All right, getting us used to seeing all the different ways they can ask us a question. But I believe you'll begin to see patterns, which is nice, okay? All right, so let's look at the first one. All right, so fish enter the lake modeled by the function E of t given by, there you go. Fish leave the lake at a rate modeled by the function L. These are both rates. What does that mean is true about E and L? They're derivatives, okay? They are derivatives. Okay, E and L are both a derivative. That's important. That word means a lot. That means when I take an integral, it's going to give me some accumulated change. Okay, both E and L are measured in fish per hour, and T is measured in hours since midnight. Okay, for part A, how many fish enter the lake over the 5-hour period from midnight to 5 a.m.? Give your answer to the nearest whole number. That's the first time that's ever, you've probably seen that. Okay, they don't want your decimal approximation there. All right, what would you do? Yes, but what's it only asking me about? How many enter? Okay, so I don't need both functions. I just need the one where they're entering. Okay, I'm going to find out how much change that was. So from 0 to 5, and you can actually just write, because it's calculator, E of t dt, put it in your calculator and get an answer. Okay, you don't have to write that whole function out. All right, they know, they told you what E of t was. Okay. How many fish would we write as our final answer? 153 fish. All right, enter the lake. Okay, there you go. All right, I like this one. What's the average number of fish that leave the lake per hour over the 5-hour period from midnight to 5 a.m.? Okay, so do we care about how many are coming in? Nope, we just care about who's going out. Okay, so 0 to 5, L of t dt. How would I handle the average? Divide the whole thing by 5 or put a 1/5 out in front? Yeah. To do the average, we're going to divide by 5 because we want it for every hour. So there were 5 hours. We divide by 5. Good. This time it didn't say round, so we'll take 3 decimal places. Okay. What'd you get? Yep. So 6.059 fish. All right. Okay. Part C. All right. This is one that was added in, but I think it's a good place for it to be added in. Okay. This is not the actual part of the question, but it's a good question. All right. It says, at what time between 0 and 8 is the greatest number of fish in the lake? Okay. Whew. All right. So now we got to think about they're coming in and going out. Okay. So if we think about our total fish in the lake, all right, that would be A at T is going to equal the integral, all right, from 0 to X of how many come in minus how many go out. Okay. That would be my amount of fish, right? I have to use the integral because E and L are rates of change, okay? Now, to find maximums, which is what they're asking me for, a maximum, what do we have to do in calculus to always find a maximum? We have to do a derivative and find where it's equal to 0, our critical points. Good. Okay. Now, if we're finding our critical points, okay, if I take the derivative of A prime, okay, or the derivative of A, I'm taking the derivative of that integral, what will it leave me with? If I take the derivative of A, which is this integral,
It's just gonna be E of X.
e to the x minus L of x. That's part one of the fundamental theorem, so they threw that in there, all right, as a place for that to come in. And I need to know where that's equal to 0, okay? You got a calculator. You have the E and the L functions. Plug them into y equals c where it equals 0, okay? What's the x values you're just considering? 0 to 8, so we don't need to see 1.5 million different values, okay? Put it on your calculator, look at the graph. Change your window if you need to. Just do your x's from 0 to 8. So then that way you can see what you need. Okay, so you got a lot of parentheses in there. You may have to use multiples. Okay. Did you get 6.024? Okay. Now we're not finished, all right, because we have to justify. That's the only critical point. So if we're looking at that derivative graph, we could look at, if I want a maximum, it would have to be positive to the left and negative to the right. So we could do that. We could look at that. All right. But the best way to justify is that candidate's test. And that's usually what they're looking for right here. Okay. So we're talking about X, or let's say T because it's T. in A of t, right? So we know 6.024 has to be there. The other values that need to be included are endpoints. Do I have a closed interval? Yep, I got 0 to 8. Okay, now, that means I'm plugging it in up here into this integral function. All right, what's going to be the integral from 0 to 0? It'd just be 0, okay? And now you've already got e of x minus L of x in y1, right? Okay, so when you do your math 8 or math 9 to do your integral, so 0 to 6.024, just put y1 of x inside that integral. Okay, let me show you. So you're here on your home screen, okay? You've got a function in y equals, okay? This is, you know, mine's not going to match all's, but, okay? So when you do math 9, from 0 to 6.024, inside of there, just do alpha trace y1, because you've already got it in there. There's no reason to retype it, okay? So then when you do 0 to 8, same thing, you just change that boundary. It makes it a lot easier, okay? All right, so for 6.24, I think you get 135.015 and then 80.920, okay? The candidate's test is justification, all right? That's what's nice about it. Okay, we plug it into the A function, all right? And so now if we write our answer, the greatest number of fish okay, in the lake occurs 6.024 hours after midnight. Okay, so now let's transition into evaluating integrals algebraically. We're really getting to where we can do full free response questions. Okay, there's a lot more to come, all right, but we're making really good progress into that. Okay, let me give you some lesson practice to look at. You're going to need to practice some of these, especially some of the ones that are more wordy. Some of them are just basic antiderivatives. On page 305, here's some good ones, 21, 27, and 29. And on page 317, 29, 31, 33, 35, 37, 38. Okay? And go ahead, let's do your wrap up. So we'll get a couple of those this week. Okay? All right. Let's see what's happening Monday because I can't remember. Yes, dear. Yes, ma'am. That was a desperation right there. You had the potty wiggles. Yeah, we're going to look at 6.8 on Monday. Yeah. Okay. Your next quiz is next Thursday, by the way. I love that it was your screensaver or your wallpaper. Oh, yeah, gotta have Jacob in there.
Yeah.
She went.
Yeah, it was a picture that when we took the PSD.
I love it.